Hannah, and thanks everybody for joining us here on what hopefully is a beautiful Friday morning in your neck of the woods. We're starting here in Northern California. We're just starting to have some fall experience with some cooler weathers and some color in the trees, and hopefully you guys can say similarly. So we're here to talk about best practices for storage, all things operational, and really how to make your system last and run effectively, and get the most out of that sizable investment. So I've got here our subject matter expert, Brad Bassett. He's going to be doing most of the information today, and we got a lot to cover. So on that note, let's jump in. And those of you guys that have been around a while know we like to start with an agenda, just kind of lay out where we're going, what we're going to talk through. So we'll talk through the different types of storage that are prevalent out in the market. And then for each one of these, we'll talk a little bit about shipping and handling, what's important on how to get these where they need to be, and get them installed and commissioned once they're there. Quite a bit of time spent on operation and maintenance. Predominantly, we'll cover those aspects for lead acid batteries because they are more maintenance intensive, but there are some things to do for your lithium ion chemistries as well. And then, of course, to be responsible here, we'll cover end of life. So, what to do when you've used every last usable kWh out of each of those batteries, and how to dispose of them responsibly. So, Brad, we say we get this kicked off.
Okay, good morning, everyone. This is Brad, and we're going to deal with lead acid batteries, which includes both flooded electrolyte and VRLA, which is valve regulated lead acid, which basically just means sealed batteries, either AGM or gel. And then we'll deal also with the lithium ion and lithium iron phosphate batteries. And these are basically the batteries that are in use for our industry at this time. I'm not going to go into any of the other less common ones. So in each of these types of batteries, we're going to go through the shipping and handling, and then installation, commission, operation, maintenance, and then end of life. So we'll start with shipping and handling on the lead acid. And flooded lead acid batteries, liquid electrolyte, and a few of the VRLA batteries will ship as a Class 8 corrosive hazardous material. And they have a UN number which specifies the packaging, marking, labeling, shipping documents, et cetera. Most of this is going to be taken care of by the company that's shipping these to you. There are some regulations on transporting over a certain quantity of these, even if it's in your own truck, and you can look up those requirements if you are so inclined. Do keep in mind that if you're trying to ship these overseas, shipping them on an ocean liner can be quite a bit of a chore. There's a lot of packaging involved in shipping these overseas. Generally, the cost of packing them costs as much as the batteries do if you're looking at flooded batteries. But most VRLA, AGM, gel batteries can ship as non-hazardous. They can ship by air, they can ship by ocean, just as regular freight goods. So the electrolyte in the lead acid battery is going to be a solution of sulfuric acid, which is corrosive to skin, cotton, wool, etc. So you want to make sure that you're well protected with goggles and gloves and boots and maybe even an apron is not uncommon to keep that stuff off of you and off your clothing. And of course, you want to not have the battery tipped over so it can spill, which does happen occasionally. Now with the sealed batteries, you do not, of course, have this issue. You can unless the case is damaged, you're not going to have any acid coming out, and the acid that does come out is probably going to be minimal because it's absorbed or in a gel. But of course, if you have a broken battery, you've got an issue with that also. And of course, the other issue is with any of these batteries is you don't want to short the battery terminals because there's potential for literally thousands of amps instantly, which is enough to melt your tool, burn things, start fires, etc. And if the battery happens to be undercharged and producing hydrogen, of course, you could even have an explosion and blow the top of the batteries off, which would not be a good thing.
Yeah, Brad, that reminds me of the first lesson I had working with cars with my dad was we keep all the wrenches and all the screwdrivers and all the tools away from the battery, exactly for that reason.
Yep. So when you're receiving a shipment of batteries, it is a good idea to take a look at the shipment before you release it from the driver, before you sign for it. If there's any problems with the shipment, you should probably refuse it and deal with, and have the shipper deal with whatever issues there are. Although the manufacturers recommend that you check and make sure all the parts are included, which most truck drivers are going to be a little bit upset if you start unboxing it all, but you should at least know that there should be a box of hardware that comes with the batteries, perhaps. And definitely make sure there's no acid spill. If there's any acid spill from the shipment, either with flooded or with a broken AGM battery, you would definitely not want to accept the shipment, because that would definitely indicate shipping damage, or visual damage to the batteries. The flooded battery manufacturers even say that you should go so far as to verify electrolyte levels. That would be, again, between you and the truck driver, whether they're going to let you do that or not. And another thing is verifying the adequate voltage on the batteries, if it's possible to do so before accepting the shipment, and this would be something that would be more on top of the shoulders of the manufacturer, because they should be sending you fully charged batteries, at 2.1 volts per cell or higher. That's 12.6 volts for a 12-volt battery. Because anything less than that, and that battery is either discharged or not fully charged, which is not good. They should be shipped to you fully charged. Mm-hmm. And then if you're, once you've got the batteries in your possession, you should make sure that they're fully charged before you store them for any length of time. And then check the batteries regularly to see if they need a refreshing charge, because you don't want to store them for any length of time and allow them to self-discharge, because that will degrade their capacity permanently if you do so. So you want to look at the manual when you receive them and find out how long, what that period of time is between refresh charges. It's going to vary from 3 months for maybe some flooded batteries to up to 2 years for some AGM batteries. A lot of AGM batteries, 6 months to 9 months is the most common period. But it also depends on what temperature you're storing them. If they're in a cool place, that interval can be longer. But if they're in a hot place, that interval is going to be much shorter.
Yeah, all great points there, Brad, on shipping and handling. And again, the importance, I can't stress enough, of doing a proper and thorough inspection before you sign off to release the shipment. And I know drivers are great at giving subtle pressure to get a move on and get them back on the road, but they're legally required to give you time to inspect the shipment. So do your due diligence and make sure you know what you're getting before you sign on the dotted line. All right, let's move along to installation and commissioning.
So flooded electrolyte batteries are filled with the acid, and when they're charging can give off corrosive mist and flammable gas, hydrogen. So they should be installed in an isolated, ventilated enclosure with spill control. And that spill control is basically something that will hold whatever fluids happen to make it outside of the battery. And in some cases, you may even be required to put in an absorbent material underneath the batteries and have an enclosure that's large enough to hold all the electrolytes so it all spill out, or should a battery break. But do keep in mind that part of the venting for these batteries is for getting rid of the hydrogen, and hydrogen will rise in the atmosphere because it's much lighter than air. You can think of hydrogen in air as being sort of like air bubbles in water. It's going to go up, and it's going to keep going up. And so you want your enclosure designed so that that gas doesn't gather anywhere, so that it goes out through the venting all the way to the outdoors. And it does not need to be very big venting. As you have, maybe could visualize with air bubbles in water, it's going to find its way out even through the smallest cracks. And the sealed batteries, the AGM and the gel batteries, are not really going to give off any gas other than the most minute amount, unless they're being overcharged, in other words, abused. And then they may give off some gas, but the requirements for ventilation for those are considerably less. You just don't want them in a sealed enclosure. You want to have the ability for a little bit of gas to get out of them. And generally, if you have a moderately sized room with, unless it's particularly well sealed room, it should have adequate ventilation for sealed batteries. It's not uncommon to have those indoors in a garage without any particular special ventilation. And of course, flooded batteries anyway should be constrained so that they don't tip over and spill. But even sealed batteries should, if you're in an earthquake area, should be, constrained or strapped down so that they don't move around or break or the like, during an earthquake.
Brad, I was thinking about this slide yesterday. As you recall, I had a new air conditioning unit installed at our house, and the air handler up in the attic, typically you'd see installed in some kind of big steel tray. Well, now they're using plastic trays because they're lighter and a lot more cost effective. And the guys installed basically a liquid sensor that sits in the bottom of that tray, and if it detects any condensation building up, it opens up a relay on the basically the supply side to the air handler. So basically, if it detects any water accumulating in the pan, shuts off power to the air handler, and it forces you to go up in the attic and take a look. Really simplistic kind of control mechanicals there, but got me thinking here to this slide and how something like that would be very helpful. In an enclosure like that the installer and certainly the homeowner is not checking up on regularly. That if anything starts to accumulate in the bottom of that enclosure, to set a warning light or to set a relay that opens would be money well spent, in my opinion.
Well, particularly if you had a automatic watering system on a flooded battery, it might be a good idea. I mean, it's really a good idea just to be there when it's active.
Yeah.
There are some automatic ones which most people decide is not really safe enough because you really don't want to overfill your batteries. It's not a good thing.
Mm-hmm.
A lot of people put in a vent fan that's activated while the batteries are charging, and I think that there's some thought that this is to help dissipate the hydrogen and the like, but actually it really is completely unnecessary for the hydrogen. What it does is it keeps the battery bank from getting too hot, and which is a good thing if it's in an enclosure. But it also will help dissipate the fumes and the gases if you have a flooded battery. Of course, you want to use a fan made for this, so it won't ignite the hydrogen going past it. Hydrogen ignites at fairly low percentages, 4% and above. And of course, if you have a flooded battery bank, it's good to have a container of sodium bicarbonate handy, in case there's a problem. And actually, it can be used for cleaning the batteries also on the outside. You just want to make sure that you don't get any inside the battery, because it would contaminate the battery and that would damage the battery fairly severely. And also, of course, you want your battery bank to be installed where it has moderate temperatures, because cold temperatures will reduce the performance pretty severely, and higher temperatures will degrade the lifetime on lead batteries quite rapidly. Anything over 90 or 100 degrees, and you're going to cut your life of your battery bank in half or worse.
Mm-hmm. Yeah, I'd say probably 20% of the questions I've ever fielded on storage had to do with will they work at this temperature, or, is this too hot or is this too cold? And again, your mileage may vary according to the specific chemistry and the manufacturer, but I think across the board, it's safe to say that temperature is a big factor in the in the lifespan of a battery bank, and how much, how far that investment will go. And it's cheap insurance, I think, to make sure these are going to go in a moderate temperature environment. And if you're going to have harsh conditions facing that bank, if it's in a power shed in the northern climates, there are options for insulated enclosures to help protect these from the elements.
There are also batteries made specifically for longer life at higher temperatures. Unfortunately, those are mostly for backup power and not for off-grid or deep cycling.
Yeah.
So as far as a design of a battery system, at least with lead batteries, it's general practice not to parallel no more than 3 strings of batteries in one system. And actually, it's better to have either 1 or 2 parallel strings, because these batteries have no active balancing mechanism, and more than 3 strings in what people have found is that it introduces imbalances that may degrade the life of the battery bank. Some of them are going to get more charge than others, and then some of them will get overcharged, and some will not get an adequate charge. So it's best to keep those to 3 strings. And of course, new batteries or a different kind of battery should never be added to an existing battery bank, because that introduces an immediate imbalance, and the new batteries will not get adequately charged, and the old batteries will get overcharged, and both the new and the old batteries will fail prematurely. And you want to keep your wiring all pretty much oversized and the same current path to each string, which basically means that you need to keep the cables the same length. You need to connect up. If you have parallel strings wired together, you want the positive to your inverter on one string and the negative on the other string or the third string, in order to keep that all balanced so they all see about the same current. And you need to do that. The traditional way in the solar industry is just to have parallel cables between the strings, but the other industries do it a little bit more robustly, where you have the same length cables from each string going to a common bus bar. And you want to be aware of the corrosion potential for flooded batteries, and use some terminal protector grease on the wiring and terminals to keep those connections low resistance. And there's lots of different kinds of terminals, so you want to make sure that you're connecting them properly. The manufacturer's instructions are going to tell you where to put the washers and where to put the battery cable connectors and the nuts and what to torque them to, and that should be adhered to, particularly if you have lead terminals on your batteries.
Mm-hmm. Brad, for periodic maintenance, would replenishing or reapplying that terminal protector be a good idea, or is that overkill?
I'd say it's probably overkill. If you note corrosion on a connection, you should redo the connection, take it apart and redo it and re-grease it.
Yeah.
But if there's no corrosion, I wouldn't. You might want to check the torque on it occasionally, but otherwise I wouldn't necessarily want to put more grease on it.
Makes sense.
Okay, once you you want to make sure that the charging voltages and maximum currents and the like are set on your inverters and your charge controllers, so that the batteries get an adequate charge, but not overcharged or undercharged. And you want to make sure that they're kept fully charged and given regular refreshing charges until they're put into service. And some batteries also require an initial charge, as sort of like a small equalization, or just a certain amount of, up to a certain voltage for a certain amount of extended amount of time, just to sort of form the plates, make sure that they're ready to start service.
Makes sense.
And we touched on temperatures before. Here's a little chart that shows what happens when the batteries are cold, and it depends on what rate you're discharging them at. If you're pulling a lot of power off, the temperature is going to have a greater effect than if you're pulling power off at a slower rate, as you can see in this chart. And also, batteries want to be charged at a different voltage depending on what temperature they're at. And so you should use the temperature sensor that comes with, or get a temperature sensor for your charging for your inverter or your charge controller. Most inverters come with a temperature sensor. Not all charge controllers do, but you should use them. And then I know that some instructions indicate that you should put that temperature sensor on the battery terminal where the cables are connected, and I do not agree with that, even if the manual says you should, because those connections can get hot when you have a lot of current going through them. And what you really want to measure is the temperature of the battery itself. And so I consider it better practice to put that temperature sensor pushed up against the side of a battery, generally in the middle of the battery pack. And a lot of these sensors have double sticky tape on the back of them, which works great. Just stick it on a battery in the middle there somewhere, or you can put a little piece of foam or something between two batteries that sort of pushes the thing in there, or you can just tape it on, and that'll adjust the the charging system to the correct voltage for the battery for the temperature that they are at.
So Brad, I've got a temperature related question for you, but it's probably best asked on this slide here. So obviously we know with inverters there's manufacturer recommended spacing, minimum requirements for spacing between units to ensure proper airflow, et cetera. Do you see the same types of things with batteries? The reason I asked here is, we've got a high capacity battery bank set up here, where those cells are packed in really tight. I'm curious if you've seen different requirements from different manufacturers on spacing between cells.
Sometimes they do give a recommendation for keeping space between the cells. And you can't really see that on this particular photograph of a battery bank, but that battery bank actually does have a pretty good space between the cells. When you have a rack from the manufacturer like this, they'll of course make it, design the rack so that there is space between the cells. Some of them have very minimal space, but I know that this company does put space between the cells. And some battery manufacturers recommend that. Some of them don't necessarily recommend that, but it's probably a good idea. So one of the most important operational considerations on almost all lead batteries is that they need to reach 100% state of charge every few days, if not daily. You can go for a week, occasionally, without getting it to a full state of charge, but you really do need to get it to a full 100% state of charge, because running those batteries at a partial state of charge, continually, in other words, where you don't get up to a full charge for weeks at a time, will make the negative plates build up sulfate crystals, which is called sulfation of the negative plates, and that will permanently degrade the capacity of the battery. And if it's severe enough, it will reduce the life of the battery to a matter of months, and reduce the capacity. I mean, I've seen batteries where easily gone down to about 10% of its original capacity after leaving it for a couple of months without a full charge. And there's really no way to recover that. I mean, there's been a few purported ways of doing it in flooded batteries in the past, but they don't really work. That's really one of the most important things that you and the person operating the system, especially if it's an off-grid customer, is that those batteries do need to get up to a full state of charge every so often. And there are some newer batteries with the carbon enhancement, nanocarbon and the carbon negative plates that are more tolerant of partial state of charge. So you can go for a week or two without getting up to a full state of charge, the sulfate crystals are not hardened as much when you have that carbon in that plate. But it's still a good idea to bring up to 100% state of charge, at least once a month or every couple of weeks, just to get the cells balanced and make sure they're in good shape. You need to sort of go through with your customer what it actually takes to bring a battery to 100% state of charge, because some people think, oh, well, I charged it for an hour or two, and it got all the way up to the absorbed voltage, and so it's all charged. But that is not true. If your battery is at lower than 50% state of charge, it is going to take at least 5 or 6 hours, and if it's lower than that, more like 8 hours to bring it to a full state of charge. Lead batteries do not charge faster than that, regardless of how much power you think you can put into it. When you are charging it and you get up to an absorbed voltage, and then you see the charge current taper off and to the point where it doesn't really drop anymore, then that's where you've got 100% state of charge. And I think we've got another slide that goes through this a little bit more too.
Yeah. Another one of my little folksy anecdotes here, Brad, and that's that, when working with my dad, he'd hook up his trusty old battery charger to cars. And I'd say, well, how do you, me, kid of the 80s, like, how do you know when it's full? There's no light. There's no green light that turns on. He says, well, you just got to wait till the ammeter drops down below 1. And, the charger knows the battery's full. Oh, okay, Dad. And
yep, you got it. That's it. So there's a few ways to actually figure out what the state of charge is on a lead battery. With a flooded battery, you have access to the electrolyte, and you can use specific gravity, meter, and it does need to be temperature compensated, or it's not very useful. But it's a messy job. You have to you're dealing with acid. You're pulling acid out of the battery and putting it back in, and with glass tubes and the like, and so you do want to take adequate safety precautions because you're working with that acid electrolyte. People don't do this very often just because it is such an onerous process. Or more commonly, you can use an amp hour meter, and a lot of the inverters and charge controller systems have built-in battery capacity meters now. Amp hours are basically an amp hour meter. They're measuring how many amp hours you've taken out of the battery, how many you've put back in. They're adjustable for different ratios because it's not a one-to-one ratio, pulling out and putting back in. And some of the older ones were, you had to adjust all this yourself, and it was a little bit difficult to program. The newer ones are a little bit smarter, and they can tell. They sort of have more smarts to can tell when the batteries are full, and they can reset at 100%. You can also do this just by sort of seat of the pants, estimate the approximate charge by looking at the combination of whether it's charging or discharging, what the voltage is. And back in the real early days, this was commonly done. You would live with your system for a while, and you just sort of get an idea, it's 5 in-the-afternoon, it's been charging all day, I've got a load on it now, the voltage is 12.8, and you'd have an idea that, well, maybe I'm at about 90% state of charge. But it's rough, and it takes experience with your SAS system and a lot of attention to really get to the point where you can have an idea of what's going on. So it's much better to use an amp hour meter or battery capacity meter for most systems. That's what most people are going to find acceptable.
So Brad, you and I were having this conversation this week about a little troublesome system that we've been trying to diagnose over the past couple months, and we were talking about how we could get a rough estimate of the remaining capacity in this battery bank by installing an amp hour meter. But knowing that this bank's been installed for the better part of a year and perhaps has had some trauma. So your process there that you'd recommended to the customer was to well, can you walk us through briefly what you had recommended to get a usable capacity estimate from that battery bank?
Yeah, really the only accurate method of figuring out how much capacity your battery bank has is to fully charge it and then run it on a given load or a measured load until it's depleted. There's really no other, there's the battery meters that the car auto repair places will use, that puts a big load on that. Well, that's a good way of evaluating a battery, whether it can start a car or not, but it doesn't really give you the total capacity of the battery. So if you have an amp hour meter on your system, you just give it make sure it's got a full 100% state of charge, and then run it down until you're at some, predetermined lower voltage. And to get a real number, the battery manufacturers run it really dead to various different voltages depending on how fast you're discharging it. But if you run it down to, say if you have a 48 volt battery bank, if you run it down to 47 volts or so, you've got most of it there, and it'll give you a good idea what your capacity is. You don't have to run it all the way down, which isn't very good for them. And most of these amp hour meters have some sort of programming in them so that they, know how much state of charge you have when you've started charging them again. And so when you're doing a test like this, you don't want it to charge at all. You want it to discharge only from full to empty. And if you have an amp hour meter, it doesn't have to be a steady load. If you don't have an amp hour meter, you do have to have a steady load, and you have to know what the amperage of that load is, of course, in order to figure out how many amp hours you have in your battery bank.
So that sounds like a pretty straightforward process, but the obvious inconvenience there is you've basically got to have load only and not charge that bank for a period of time, and I guess the period's dependent upon how large the system was sized relative to the loads. And then when that test process is done, you've got a depleted bank that you're not going to be able to put a load on until it gets charged all the way back up again. So simple in theory, but probably a lot harder to execute in a practical environment.
Yeah, and it can take a day to do that test.
Yeah.
Or you can do it. Sometimes you can do it faster if you have the loads available to do it faster. Okay, so with flooded batteries, it's a good idea to do a regular equalizing charge, and this is basically just an overcharge. So you charge the batteries all the way up, and then you give them another booster charge at a little higher voltage, and this balances the cells, and if it causes the electrolyte to bubble and mix so it doesn't stratify, so if you don't do this every so often, the more concentrated acid will drop to the bottom of the battery and less concentrated acid at the top, which would not be good for it. And if you happen to have catalytic caps on the batteries, you have to remove those while it's doing an equalization charge. Otherwise, they get too hot and melt, which is not a good thing, especially considering what they cost. With sealed batteries, you don't give them these charges because you can't replace the water in them, so you don't want to be boiling the water out of the battery. So they're not made for that, and they have a different alloy structure in their plates so that they don't need to have this equalization. And of course, the electrolyte is either absorbed or gelled, and so it's not going to stratify. And you can follow the manufacturer's guidelines for this. I mean, it doesn't hurt to give them sort of a little bit of a boost now and then, depending on how they've been treated. But generally, they don't get an equalization charge.
Brad, how long does the equalization charge typically take?
A couple of hours, I think, is common.
Okay.
And of course, with flooded batteries, you're losing water from the electrolyte as they're charged. And you do want them to lose water from the electrolyte when they charge. You do want that level to go down because they're not getting an adequate charge if it's not. So that's a good indication that if you have to add water to your batteries about once every couple of weeks or a couple of months at least, then you should be probably charging them harder than you have been. And it does need to be refilled and with distilled or deionized water. And you want to be very careful not to overfill the cells because then your electrolyte density is thrown off. And then you've got an imbalance between cells, which is a problem. And of course, the flooded batteries, you've got acid mist that'll settle on the top of the batteries, which is ugly and causes leakage currents, which hastens self-discharge and produce corrosion on the battery terminals and the like. So you can use the sodium bicarbonate to clean the batteries, from this acid mist that's built up on them. But of course, you want to be careful not to get any inside the battery that will contaminate them. And this picture shows a semi-automatic watering system. It's basically, it's got these tubes that go on all the cells, and there's little float valves in each cell so that they don't get overfilled. And then you just turn on the water, you plug the hose into the tubing there and run the water until they're all filled, and then you take it off. And if you're there while you're doing that, you make sure there's no bad float valves so nothing's comes pouring out. It's really sort of the easiest and best way to maintain a flooded battery bank.
Sure seems like a ton of work, Brad.
Yeah, it is, and that's why we're finding fewer and fewer people using flooded batteries because they're just sort of a real pain to deal with. And I mean, I would never put another flooded battery bank in my system. It's just I got tired of dealing with that and don't want to deal with it anymore. And there's a lot of AGM and gel batteries that are as good or superior to the flooded batteries in a lot of cases. So it's generally worth the extra cost to get the sealed batteries over the flooded batteries anymore.
Yeah.
Yep. So lead batteries have one really big advantage over anything else, and that is that they are almost completely recyclable. And because the process for recycling lead batteries is so ubiquitous, it's probably the most recycled product made. I think somebody said something like 98% of all batteries are recycled, or I don't know, maybe something close to that, and 98% of the battery gets recycled into new batteries. So that's actually one of the few closed loop product cycles in that we have. But if you're going to, at the end of life of the batteries, you want to discharge the batteries to the extent possible. That makes them less hazardous, in case somebody shorts out the terminals or the like. So you want to be careful. You don't want to short them out, while they still have any oomph in them. So you want to put a load on them. Just run your inverter, run them down until they go dead, and maybe even lower the LBCO, low battery cutout voltage, and run them down even farther. And then if you want to, that's probably adequate for most recyclers. And then I already touched on the recycling. There is generally a core refund, and it can be a noticeable amount of money. About 200 amp hour 12 volt battery will bring $20-25 each when you bring them in for recycling. So it's nothing to sneeze at. It's enough to make it worthwhile to get them in there and get them recycled.
Mm-hmm. So as we transition to this next slide, it's going to take us into the lithium iron phosphate portion of this webinar. And for me, Brad, as we were putting these slides together, it was almost like two different books, and you had to forget most of the first book when you moved to the second one, because so many of the rules of thumb around, for instance, they're highly recyclable. They need to get to regularly to 100% charge and stay there for a while. So many of those rules of thumb just don't apply to lithium and are actually, counterproductive on the lithium pack.
Yep. So the lithium batteries that we sell and talk about here are generally fall into two different groups. And I'm going to call one group the lithium-ion batteries, which is generally a variety of chemistries, NMC or NMALC and various different ones. They're similar to the battery cells that are used in electric cars. And they generally have an output voltage that's matched to an inverter that they are made to work with. So they're matched. You don't just buy an inverter and buy a battery. You buy an inverter battery system that's made to work together. And those batteries are generally running it at least between the battery and the inverter, generally running it at 200 to 600 volts. 350 is common. 380 is common. These are like the LG Chem and the Generac and the Tesla, BYD, Panasonic type batteries fall in this type. And then there's the lithium iron phosphate batteries, which are usually sold as a nominal 12, 24, or 48 volt battery to use with whatever inverters or chargers that work with those nominal voltages. And so they're not always matched specifically to an inverter or a charge controller or to loads. So you can take a system that's been using lead batteries, and you can actually substitute these lithium batteries for the lead batteries in that system. And you just have to change a few set points to make it work. And so these are like the Discover battery that we sell, and then there's also Fortress and Simplify, and the Enphase is sort of a special AC coupled version but they are also using lithium iron phosphate.
So in the early days of our carrying Discover, I was billing those as a drop-in lead acid replacement, which man, looking back was definitely short selling their capability.
Yeah, to some extent. So lithium batteries are also considered a dangerous goods, and they don't separate lithium iron phosphate from the other lithium ions, although they may at some point. It seems like they should, but at this point they don't. They are all shipped as dangerous goods with a different UN number than the lead batteries because there are different requirements because they do act differently. So there is specific, packaging, marking, labeling, shipping, et cetera, et cetera. And again, when you receive a shipment, you want to look at whether the parts are there. You got a box of parts and that there's no visual damage to the batteries. You can't really check voltages or electrolyte and you certainly don't want to see anything leaking, which would be unlikely. But if you did, you certainly would consider that to be a problem. They're usually shipped partially charged. They don't need to be kept full, and they're a little bit safer when they're partially charged, but they don't want to be dead either. And then if you're going to store them, you want to make sure that they're kept, at a moderate partial state of charge. You don't want to let them go dead when they're in storage, and that can be anywhere from 90 days to up to a year or more in some batteries. It just depends. You'd want to check with the battery manufacturer to find out, how often you need to check them.
Yeah, so for me, this was one of the biggest differences between the lead acid chemistries and the lithium ion. And particularly for the LG Chem Resu 10H, we had to dig into this a couple of years ago to answer a customer question about shelf life. And so those packs shipped from the factory with a 30% charge, which the target, call it terminal voltage at the DC-DC converter was somewhere between 152 and 156. And anything below 137 was considered dead and not recoverable. And the test procedures for charging there were very specific about how long to charge, at what current, and when that battery would be considered back up to a 30% state of charge again.
Yeah, and if you go too far, if you go too low on lithium cells, and this doesn't not even matter which kind of lithium cell, but any cell, if you get too low, too close to absolute zero on that, you've destroyed the cell.
Yeah.
You can't recover them. And same thing, if you go over a certain voltage, you've destroyed it. There's no recovery from it. So you do have to be careful with that. So for installation, because you've got a battery, well, at least with the lithium ion, you've got a battery that's specific to the inverter. You do want to be looking at the manual and looking at the specific instructions that they give you for installing the battery and the inverter together. And you do want to put these in a place where they're protected from physical damage, because they do not do nice things if they've been crunched or smashed or poked or anything like that. So you don't want to put it someplace in a garage where somebody can accidentally, when they come home a little bit south one night, hit the battery with their car, because that could very easily start a fire. And some of these are outdoor rated, some of them are not. But of course, they're still sensitive to being really hot, so you don't want to put them where they're going to be in direct sunlight if you can help it. And actually, it's probably a good idea not to put them where they're going to be directly rained on either, although some of them are okay with that. The lithium iron phosphate batteries are generally not outdoor rated. They just haven't gotten to where they need that at this point. Haven't done it yet. And you want to be careful about where they're installed as far as temperature goes. The lithium batteries do generally have the longest life and best performance if they're kept within a certain narrow range of temperature. At least for one of the batteries that we sell, they recommend keeping it between about 60 and 80 degrees Fahrenheit, although the temperature where they will function all right is generally between somewhere around freezing to about 114 or 116 degrees Fahrenheit. But they're going to last a little longer if you can keep them at a moderate temperature. None of the lithium battery cells that are in the market at this time can be charged when they're below freezing. Now, some of them will have internal heaters, or will have a circuit that prevents charging when they're cold, so that they can be installed in a place where there's a wider temperature range. But they're going to be either using energy to heat themselves up or not charging when they're cold. So you wouldn't want to put them in that temperature for any length of time, because it's going to degrade the performance of the system. And the lithium batteries do not need to have their charging voltage adjusted for temperature like lead batteries do. And so you would not want to install the external battery temperature sensor that comes with inverters and charge controllers. You want to leave those off and unplugged, so that they charge it only at the specified voltage, which is fine over their entire temperature range. Most lithium batteries have an internal battery management system that has their own thermometer on it. So at least if you have external communications to that battery, it'll tell you what temperature they're at, which just means you can keep track of whether they're being overheated or not.
This reminds me, Brad, of one of my oft-repeated statements about lithium ion and lithium iron phosphate is that a big part of the value, if you will, of what you're buying is the reliability of that battery management system, that it's got good quality components, that it's taking accurate temperature readings, and that it's monitoring these things for you, in that enclosure.
Yeah, they're because you've got electronics in that battery. Electronics can fail. Of course, the reliability of that is another factor, and one that you want to pay attention to. Some people put together their own lithium battery systems, and they buy the battery management systems, third party, and you don't really know what you're going to get into with that. You don't know if you're programming it correctly, if it's going to really adequately protect the battery, et cetera, et cetera. And I know a lot of people have gotten in a lot of trouble with trying to do that.
Mm-hmm.
Anyway, your power and communication wiring, you just follow the manufacturer's guidelines on those. And if you're using a lithium iron phosphate, configure your inverter for use with that battery. same as you would for lead batteries. It's just that the set points are going to be a little different. Now, if you've got a closed loop communication, like say Discover to Schneider, or all the lithium ion types, a lot of those parameters are going to be set automatically when you have the communication set up. But you should make sure that the system is designed so that your voltage, current, state of charge limits are not exceeded. Design your system so that you don't get too much charging current, and make sure your voltages are all set accordingly. And then there's the recommended operation ranges. If you can keep the batteries functioning within the recommended ranges instead of the maximum minimum range, it'll just enhance the performance and the lifetime of the battery. And same as with lead batteries, you want to keep your cabling installed so that each battery gets an equal length, equal balance of charge and discharge current between them.
Mm-hmm.
With some of the lithium iron phosphates, a lot of the wiring ends up being sort of similar to the lead batteries in parallel. And the lithium batteries are generally, each unit is generally at the voltage that you're using it at. In other words, if you have a 48 volt inverter, you're going to have a 48 volt battery, and they all are operated in parallel. And very, very rarely would you ever put lithium batteries in series, and only when it's recommended by the manufacturer.
Mm-hmm.
And lithium batteries do not have the requirement to be fully charged all the time, not like lead batteries do. They like being run at a partial state of charge, anywhere from almost depleted to almost full. They like running in anywhere within there. The lithium iron phosphates are okay being kept at a full state of charge if the voltage isn't too high. But you want to be careful not to operate them at a really low state of charge, because if they get down to a very low state of charge, they'll turn themselves off. But once they have turned themselves off, they will continue to self-discharge internally. And if they get too low, then they will damage the cells and won't be recoverable. So you want to be careful about not running them too low. And very important, if the system is being installed but it's not being put into operation yet, you want to make sure that battery is turned off, because when it's on, the battery management system is drawing current from the battery, and it will self-discharge at a higher rate, and it'll just discharge itself until it's killed itself. And so if you're leaving the system, in operational, you want to make sure that battery is turned off. And all these lithium batteries have an on-off switch, so that you can turn them off. And it puts the battery management system in standby and draws very little current. Monitoring of lithium-ion batteries is going to be limited to maybe a few LEDs on the battery, but they're connected to a specific inverter, and so the inverter is going to show you the battery status, state of charge, and all that. And lithium iron phosphate batteries can also do the same thing, or sometimes they have their own monitoring, like this Discover Link will give you a battery state of charge on their little graph there, or you can connect it to inverter systems, some of them, many of them now. There are some lithium iron phosphate batteries that do not have any external communications, and at that point you're relying on an amp hour meter or the like to give you the state of charge, because the voltage is not going to give you that except when it's full or empty. So anywhere in between, your amp hour meter has to be able to track that, and a lot of those are made for lead batteries, and they don't track lithium batteries well at all. Some of them are okay, but a lot of them are not. And so it's really much more useful to have a lithium iron phosphate battery that has external communication, so you can see what's going on, somewhere, so you know what your state of charge is. It seems to me it would be pretty important. Periodic inspection of lithium batteries is really, there's not much to it. You just want to check to make sure it hasn't been damaged, or cables aren't fraying or the like. There's not much to it, which is a nice thing.
Mm-hmm. All right, let's talk about the sad part, the end of life.
Yeah, well, manufacturers will tell you how to decommission the battery bank, how to turn it off, how to disconnect it, how to pack it, your packaging and shipping of that is still going to be the same as if it were a new battery. And there are currently, I've been reading, there's some startup companies that are looking at bringing in lithium batteries for recycling and figuring out how to recycle them. At this point, it's somewhat limited what your options are on that. If you do need to dispose of them, of course, they are hazardous waste at this point. So we're hoping that the recycling takes off and is able to take care of these batteries once they're at their end of their life.
Yeah, there's room for innovation there, as we would say. Awesome.
Yep.
Well, Brad, that was jam-packed with a ton of information. We've got a little bit of time here for some questions and answers. So I think Hannah, we'll open it up to you and see what's come in.
Great, thanks, Brad and Josh. And we did have some great questions come in. And so if anyone else has any questions, we might not have time to get to many more on this call, but as you can see on the slide, you can go ahead and email questions to tech@aeesolar.com, and we'll get those questions answered for you. And this webinar is recorded and will be on our YouTube channel later today, so you can always watch it again.